Hey there, and welcome back to the Deep Dive. This is where we take a stack of information, really get into it, and pull out the key ideas, the things that make you think, basically everything you need to get properly informed on, well, a fascinating topic. Today we're looking at something pretty fundamental, things that help us see the world, both the incredibly huge and the incredibly tiny. We're diving into optical instruments. We've got some great material here, really laying out the basics of how they work, what they let us see, and why they're just so important, sort of extensions of our eyes, really.
Exactly. That's a great way to put it. Optical instruments are kind of like cheats for our vision. They bend light, focus it, use lenses to show us details we'd otherwise miss, or bring distant things much closer. They help us get around the natural limits of our eyes.
Okay, so let's start right there. What is the basic problem? Why can't we just see, say, bacteria? Or why does a distant star look like just a point of light?
It really boils down to this thing called the visual angle.
Visual angle.
Yeah, think about lines drawn from the top and bottom of an object straight to your eye. The angle between those lines, that's the visual angle. Now, if an object is really small or really far away, that angle gets tiny.
And a tiny angle, Mia.
It means the image formed on your retina, the back of your eye, is also tiny. And your brain basically interprets that tiny image as small object or faraway object.
Ah, okay. So the instruments don't magically inflate the object itself. They're manipulating that angle to make the image on our retina bigger.
Precisely. That's the core job. Increase the visual angle that the object appears to have from your eye's perspective. A bigger angle means a bigger retinal image, which our brain sees as magnification.
Right, and this increase, that's the angular magnification you mentioned.
That's the one. It's the key number for figuring out how powerful an instrument is because it directly relates to how big the thing looks to you.
Okay, let's unpack this. The simplest instrument first?
Yeah.
It's a magnifying glass. Everyone's played with one, right? What's the physics there?
Fundamentally, a simple magnifying glass is, well, just one convex lens, a converging lens.
And how do you use it to make that tiny print readable?
You put the object, you want to see the print, whatever, close to the lens, specifically closer to the lens than its principal focal point.
Inside the focal length. Got it. And what does the lens do then?
It creates an image that is virtual, magnified, and upright.
Okay, virtual means the light rays don't really meet there, but our brain thinks they do.
Exactly. Your brain traces the diverging rays back to a point, and that's where you perceive the bigger image. And upright just means it's not flipped upside down.
Makes sense. Now, the materials talk about normal adjustment and the near point for this. What's that about?
Right. So the standard way, the sort of comfortable way to use it, is to position things so that this virtual image appears at your eye's near point.
Near point. That's like the closest you can comfortably focus.
Uh-huh. For most people, we usually take it as about 25 centimeters. When the image is formed there, it's the largest clear image you can see without straining your eye muscles.
And the magnification, the power of the glass, that depends on?
It depends on that near point distance, D, and the focal length, F, of the lens itself. The formula basically shows that a shorter focal length gives you more angular magnification. That's why strong magnifiers feel quite thick and curved.
Okay, so one lens gets you so far. But what if you need, like, way more magnification to see things like cells or microbes?
Yeah, for that level of detail, you need to step it up. You need a compound microscope.
Compound, meaning more complex, more lenses.
Exactly. It uses two main lenses or lens systems working in tandem.
Okay, how does that give you such a massive boost in magnification?
It's like a two-stage rocket. First, you have the lens closest to the specimen that's the objective lens. It's designed with a very, very short focal length.
And what does that objective do?
It takes the tiny object and produces a real, inverted, and already magnified image. This is called the intermediate image, and it forms inside the body tube of the microscope.
Okay, so stage one, a real, upside-down, bigger image formed inside the tube. What's stage two?
Stage two is the eyepiece, the lens you actually look through. It's positioned so that the intermediate image created by the objective falls within the eyepiece's own focal length.
Ah, wait, so the eyepiece is basically using that intermediate image as its object.
You got it. The eyepiece then acts just like a simple magnifying glass, taking that already magnified intermediate image and magnifying it again.
So you're magnifying a magnification.
Precisely. That's the power of compounding. The final image you see looking through the eyepiece is virtual, it's highly magnified, and it's still inverted compared to the original tiny object on the slide.
And normal adjustment for this. Still the near point.
Typically, yes. For comfortable viewing, you adjust the focus so that this final virtual image appears at that 25 centimeter near point.
This is where it gets really cool. So the total magnification, how do you calculate that? Is it just adding the two magnifications?
Oh, it's much better than adding. It's multiplication. The total angular magnification of the compound microscope is the magnification of the objective multiplied by the angular magnification of the eyepiece.
Wow, okay. So if the objective is, say, 40x and the eyepiece is 10x.
Then the total magnification you're seeing is 40 times 10, which is 400 times. That multiplicative effect is why these instruments let us see things utterly invisible to the naked eye.
That makes a huge difference.
Yeah.
Okay, so we've conquered the very small. Let's swing the other way completely. What about seeing things incredibly far away? Planets, stars, galaxies.
Right, now we're talking about telescopes. They're also optical instruments, obviously, but designed for viewing distant objects clearly. The source focuses on the Astronomical refracting telescope, which also uses two lenses.
An objective and an eyepiece again. How are they different from the microscopes?
Yes, still an objective and eyepiece, but their characteristics are quite different. The objective lens in an astronomical telescope, the big one at the front, it has a long focal length.
Long focal length. Opposite of the microscope objective. Why?
Because the light rays coming from distant stars or planets are essentially parallel when they reach us. The long focal length objective gathers these parallel rays and brings them to a focus, forming a real, inverted, intermediate image. According to the source material, this image is also described as magnified, and it forms near the objective's focal point.
Okay, so a real, inverted, and magnified intermediate image, again, near the focal point. Still feels a bit like the microscope setup in principle.
The principle of forming an intermediate image is similar, yes. But here, the goal is gathering light from afar. Then comes the eyepiece, which has a short focal length, much like the microscope eyepiece or a simple magnifier.
Yeah, it looks at that intermediate image.
Exactly. The eyepiece is positioned so that the intermediate image formed by the objective falls just inside its focal point, so the eyepiece magnifies that intermediate image.
Giving you the final view, what's that like?
The final image you see through the telescope is virtual. It's magnified compared to how the object looks with the naked eye, and it's inverted relative to the original distant object.
Okay, inverted makes sense if the intermediate image was inverted. What about normal adjustment for looking at, Jupiter? Is it the near point again?
Good question. No, for telescopes, especially for astronomy, normal adjustment usually means setting it up so the final virtual image is formed at infinity.
At infinity. Why is that helpful?
It allows your eye to be completely relaxed while viewing, just like when you're gazing at the horizon or the night sky naturally.
Yeah.
It's much less strain for long observation sessions.
Makes sense. And the magnification in that relaxed image at infinity mode.
In normal adjustment, the angular magnification is actually a very neat formula. It's simply the focal length of the objective lens divided by the focal length of the eyepiece lens. So long objective focal length, short eyepiece focal length, that's the recipe for high magnification.
So M equals F objective over F eyepiece. Simple enough.
Yes, and in that setup, the distance between the two lenses is just the sum of their focal lengths, faux plus fe.
Now, for seeing really faint stuff like dim nebulae, magnification isn't the only story, is it?
Absolutely not. You've hit on a crucial point, especially for astronomy. The light-gathering power of the telescope is paramount, and that depends entirely on the diameter, the aperture of the objective lens.
The bigger the main lens, the more light it collects.
Exactly. A bigger objective lens acts like a larger bucket catching faint light. It can collect vastly more photons than a smaller lens, making faint objects appear brighter and allowing you to see things that are simply too dim for smaller scopes, no matter how much you magnify them. You need light first, then magnification.
That's a really important distinction. Size matters for brightness, too. Okay, one more detail from the materials, the eye ring. Sounds specific. What is that?
Yeah, the eye ring, sometimes called the exit pupil. It's a particular spot just behind the eyepiece on both microscopes and telescopes.
And why does it matter?
It's the place where all the light rays that have successfully passed through the entire instrument converge before spreading out again. It's essentially the image of the objective lens formed by the eyepiece.
So that's where I should put my eye.
Precisely. If you place the pupil of your eye right at the eye ring, you capture the maximum amount of light coming out of the instrument. This gives you the brightest possible view and lets you see the entire field of view at once. Move your eye too close or too far away, and the image will look dimmer, or you'll only see the middle part of it.
Yep.
It's the optimal viewing spot.
Right, finding that sweet spot. Okay, so let's pull this all together. We've looked at simple magnifiers, compound microscopes, astronomical telescopes. They all seem to use lenses in clever ways to bend light.
They do. And the fundamental goal, as we said at the start, is always to increase the visual angle of the object, whether it's tiny and close or huge and distant. This makes the image on your retina larger, tricking your brain into seeing it as magnified.
They overcome our natural limitations, letting us see the unseen. Microscopes revealing tiny structures, telescopes bringing the cosmos closer.
Exactly. It's all about harnessing the physics of light and image formation, real images, virtual images, focal lengths, magnification, using these principles to extend our senses in remarkable ways.
It really does make you appreciate both the technology and our own built-in optical system, the eye, which, thinking about it, also uses a lens to form an image, right?
It absolutely does. Our eye's lens is a converging lens system, and it forms a real image on the retina. And interestingly, just like the intermediate image in a microscope or the final image in an astronomical telescope, that image on your retina is actually inverted. It's upside down.
Whoa, okay, so everything I'm seeing right now is hitting the back of my eye upside down.
That's what the physics tells us.
Right then. Here's something for you, our listener, to chew on after this deep dive. If the physical image projected onto your retina is inverted, how on earth does your brain manage to flip it around so seamlessly that you perceive the world as perfectly upright? It's a fascinating puzzle where the optics ends and the neuroscience begins.